Thank you so much for joining our CIVA 2025 webinar. We will be covering the new features within CIVA 2025 today. There's been 2 webinars already, and this will be our last webinar for CIVA 2025. With that, we'll be doing a brief introduction to the company and then covering some of the latest new modeling features in CIVA 2025 for the following modules. Then we'll be ending this session addressing your questions using the Q&A tool of Teams. So a brief overview of the company. EXTENDE is the CIVA distributor worldwide. We handle the technical support for CIVA. We also do all the training courses for CIVA, as well as we have a dedicated training course for reliability in NDE, which focuses on probability of detection studies. We also have a dedicated team of consulting experts for simulation in NDE that utilizes CIVA simulation software. And when things are out of the scope for CIVA, we also utilize a couple other softwares in order to meet your needs and find solutions to different problems you may find. We also have our training simulators for ultrasound and radiography called Trendy. And these are very, very awesome simulators that can be useful for your inspectors to train and improve their skills for ultrasound and radiography and receive immediate feedback while their level 3s or managers are not able to provide them feedback at that time, and they can keep learning and growing their skills even if they're on the field or away on business trips, for example. But today we'll be focusing on CIVA 2025. So CIVA in a few words for those that are maybe a little less familiar. So CIVA is a dedicated NDE simulation software and analysis tool. It's a multi-technique simulation software, which is great because it's very, very helpful when you learn one software or one method in CIVA, then it makes it a lot easier to learn other methods because the analysis tools are in similar areas. So it uses ultrasound, or it has ultrasound, radiography, eddy current, guided waves, structural health monitoring by guided waves, thermography, and a dedicated ultrasound platform for pipeline simulation for the oil and gas industry. It also has the ability to load in UT experimental data in our UT analysis module, as well as a data science module and scripting capabilities that are compatible with all the other modules. This enables you to use Python and MATLAB code to run the CIVA graphical interface to optimize on different solutions outside of CIVA. So there are 2 different versions of CIVA. When we say CIVA, we're generally referring to CIVA Expert, which is what we will be covering today. And then we also have CIVA Education, which is geared towards training centers and universities to help trainees and students to understand the physics behind ultrasound, eddy current, radiography, and guided wave. CIVA is developed by the CEA in France, which is the 2nd largest research facility in the world. And EXTENDE is the exclusive distributor of CIVA. This webinar is going to focus on the highlighted modules in this slide. There's quite a lot of new features in CIVA 2025, so we're just not able to cover everything in 1 hour. My goal will be to cover as much as I can in 1 hour, and I will do my best, and then there will probably be about 10 minutes or so of questions at the end. And we will have further information coming in 2026 on these topics. So CIVA UT includes the beam calculation tool where you will be able to compute your beam and your component. And then in the inspection simulation tool, you will add in flaws and predict echoes in the component. Then you are also able to calculate your delay laws with your phased array probes within CIVA. Then you have your sensitivity analysis and probability of detection tools within CIVA UT. And like I mentioned before, you can load in your experimental data into CIVA UT, and this is compatible with Edify, Evident, the Phased Array Company, and Sonatest data formats, and a couple others as well. the different techniques that are covered in the UT module or the conventional UT phased array probes, including TFM, pulse echo, tandem, and Toft. So what is new? The much anticipated and long awaited and very much so excited arrival of the finite element module perspective. So CIVA is now a finite element software, CIVA UT. And we now can validate our semi-analytical models in CIVA UT with the finite element module and explore beyond the limits of our semi-analytical module method or module of CIVA UT. We also have a new way of modeling or weld complex materials that we'll go over. And we have some new probes and wedge options, as well as some new defects. So I'm going to go ahead and demo these new features. So first thing I'm going to do is just show a quick little demo of CIVA UT and show the features at the same time. So with CIVA UT, you don't start from scratch. You always start with a component, a probe, and if there's flaws available in that module you are in, you will also have flaws. So I'm going to enter into our specimen panel. The goal of CIVA is to go through each panel and define your configuration accordingly, and then run the configuration and view your results and do your analysis. So with your specimen panel, you have lots of different geometry available. And a couple that I'm going to highlight, you have your elbow, you have a nozzle, and you can define and change the parameters and dimensions for this. And then you also have a weld configuration where you can change the bevel type. You can also make it symmetric or non-symmetric, add cladding, buttering, all those different things. And you can see as I change the weld configuration, bevel type, that it updates in the 3D view as I do that. And if the parametric options are not available, you can load in 2D CAD and extrude it as a planar or cylindrical option, or you can use the 2D CAD editor to draw your 2D CAD, or you can load in a 3D CAD as well. We are going to switch to a cylindrical option for showing our first new feature in CIVA UT for CIVA 2025. We will go to our flaw panel and add in a planar flaw. So the first new feature has to do with how we can extrude our planar and FE grid flaws. So we have a new extrusion type for cylindrical profiles called the cylindrical extrusion. This was not available before, but now our planar and FE grid flaws can follow the cylindrical profile of a cylindrical component. So this will ease the simulation or modeling of your cylindrical components with flaws. You can still tilt things accordingly and position them accordingly like you could before. This could be really good for something like a weld, for example, if you wanted to do lack of fusion or something like that. We actually have a model later on where this will be used for that. Okay, so the next new feature that I would like to show is our new flaw called our complex notch. Before, if we were modeling notches, we would use a planar flaw, but this did not have any width to it. Now we have the capability of having width, which is actually defined by this length parameter here. So I'm just going to give it some more length and some height to it. And we have a couple different profiles we can use. So we have the rectangular profile, triangular profile. We also have an ellipse. Oops. Ellipse, there we go. And we have a pencil profile that can be used. Okay. So now I'm going to position my probe in order to scan over this notch. So I can drag and drag and drop it like that, or I can go into my inspection panel, my positioning tab, and enter in the coordinates to position my probe accordingly. I'm going to go to my scanning tab and see what my default scanning looks like. And I want to get a corner trap there. So that looks about right. Go to my simulation settings panel. Half skip looks good. For my options, I'm going to compute in 2D just so it runs a little bit faster. And we'll see, we'll get this result in a second or two. Okay. So here we go. We have our response of this flaw right here, this pencil notch. So we have our corner echo and our tip diffraction right here in our A scan. If I want, I can drag and drop this B scan onto my 3D view and see what that looks like on my component. Okay. If I would like to change the color scheme off of the CIVA default color map, I can come down here and change it to something that maybe I'm a little bit more familiar with. Okay. Going back into the model, I would like to show you some of the new probe or wedge options that we have. So in our probe panel, this is where you're going to define your crystal. If you have a phased array probe, you would do that here and change to your phased array probes. If you have a different probe type and you're not in contact, like immersion or anything of that nature, or you have an EMAT, you're going to go ahead and change that here. You have focusing, or you would define your signal here. In our wedge tab, this is where our new features are going to be located for CIVA 2025. The first one I want to show is that we now have the capability of modeling an L0 probe. And we can change this wedge type to a cylindrical L0 probe. That is the first one. Now to show some other new wedge or probe features within CIVA 2025 UT, I'm going to open up this file. And we'll be looking at a dual matrix array probe. So you may have already seen it if you've been modeling, as well as in the other file I was just in. But one of the new features that we have in CIVA 25 UT is that our elements are going to have a sound propagation on the bottom of our wedge. So now we can actually see where our sound is going to exit our wedge on the bottom. This was not available before. What's really nice about this is that if we are changing something like a roof angle, I'll go ahead and change this, we'll actually be able to see how this affects how our sound exits through our wedge. It's really nice if you're modeling probes. The next new feature we have with our probes has to do with the acoustic insulation thickness with our dual element probes. So here before, it was just a flat acoustic insulation thickness. Now we're actually able to define some dimensions here for that acoustic insulation thickness. So now you see, put 2 millimeters for an acoustic insulation thickness on this dual matrix probe. And last but not least, we are now able to define wedges a little bit differently. So some probe manufacturers give different dimensions for modeling wedges. The standard in CIVA up till now has been the dimensions defined in this graph right here, with the back length and the front length and the height from the element to this exit point. But now you can select the first element configuration here and define your wedge based on the height from your first element down to the base of your wedge, which is sometimes the dimensions that the probe manufacturers give. So that will just ease in the modeling of your probes, if that's the information you're given. Okay. Moving forward. Now we will be going into our finite element module. But one last thing I would like to mention, it is not new for CIVA 2025, but for those that are new to CIVA, we do have a probe library that if you are using probes from these 4 different probe manufacturers, you can go into and find your probes. There's a little over 200 probes in this probe library, and you can find your probe and load it in and utilize it in CIVA UT. Okay. Now we will be going into finite element computation in CIVA UT. So this is included in CIVA 2025, CIVA UT. So if you have a valid maintenance contract, you will have access to this module if you have CIVA UT. The only one you may not have access to is CIVA Athena 2D. This is still an add-on module, but you will have access to the finite element beam computation and the finite element inspection simulation module within the finite element perspective. So let me open up a file and we will take a look at some of the new features or the new things that you can do within the finite element software. So the first thing I want to mention, this is the beam computation module of the finite element software. Because it is finite element, the really nice thing that we're able to now do is actually include flaws into the beam computation module and look at the interaction of the beam with the flaw. We're not generating the response of the flaw, but we are looking at how the beam interacts with the flaw. What I do want to mention is there are some limitations in the geometry. So we are limited to planar, cylindrical, 2D CAD, and weld geometries right now, with more geometries to come. And the same thing with our flaws. We are limited to a couple different flaws right now in this module. Okay, so everything else is the same. The one new thing that you need to take into account with the finite element module is the new options tab within the simulation settings. The great thing about this module is that a lot of the finite element meshes and everything are done for you. So you don't have to do that, but you need to be aware of a couple things. So you can choose 2D finite element calculation or 3D finite element calculation. And then there's a couple things to factor in here for mesh, but again, most of that's done for you. The next thing you need to factor in is the gate. So for the gate, CIVA will only compute what is in your gate. So you would define your T minimum and your T maximum. And if you know this, you can go ahead and input that in. If you don't, you can tell CIVA these are the modes I want to compute. So if you want to only compute L wave, then you check that. If you only want to compute T wave or shear wave, you check that. If you want to do both, then you check that. And then you tell CIVA how many skips, and then you can click estimate gate, and then CIVA will estimate your gate for you. The next thing that you need to take into account for this finite element module is your region of interest. So for your region of interest, you can define a full region of interest. And what this would do, as you see as I displayed my mesh across my full component. So what this will do is have CIVA calculate the mesh for the full component. This may not be necessary for your computation. So if this is not necessary, like it is not necessary in this application, then you can click custom and you can define the region of interest yourself, or you can have CIVA actually estimate it for you, because CIVA is very, very smart. And you can refine it if you would like to as well with the coordinates and everything. And I can display this mesh. What I do want to note is that you'll notice that CIVA starts this mesh in the wedge for your finite element code. And then you'll see that the mesh has an attenuated mesh in blue right outside of that region of interest on both sides. And then you can see the mesh gets really refined around that flaw. Okay. And since we're doing a 2D mesh, 2D finite element, it will actually run quite fast. So I'm going to go ahead and run this 2D finite element simulation here. And if I had I'm running this on a laptop right now. If I was running this on a heavier duty machine, it would run faster. Again, if I was running this in a 3D finite element, obviously this would take a lot longer, but the 2D finite element is actually quite fast. So. Okay. And then once this is done, we will be looking at the beam interacting with this flaw, and we will see a corner trap. And we'll also see some new things that the finite element code is able to generate that we were not able to generate previously with the semi-analytical algorithms. And I will point those out to you as well. Okay, so here are our results. Quite fast for finite element. Let me pull in my A-scan. Okay, so we have our beam interacting with that flaw. I'm going to go ahead and change this to amplitude versus time, so we can look at this as a function of time. So we can see our beam traveling through our component, and as it goes through my A-scan, it's going to hit that flaw, and then that flaw, as the sound hits, we're actually going to see a creeping wave generated from that flaw going vertically off of that flaw. That was generated with the finite element code that we would not have been able to see in our semi-analytical algorithms. I can also have CIVA actually generate a video for me of this. So we see it coming, hitting that flaw, then we'll see that creeping wave generated from that flaw. Okay. Moving on, we're going to look at a couple other new things we can do with our finite element code. Okay, so the next one we're going to look at is a Rally wave application. Let's see. Yeah. So now with our finite element, we can generate Rally waves. Before we were able to generate Rally waves with a couple limited configurations in our semi-analytical models, very, very few though. But now if Rally waves are present, they will be generated and they will be simulated with the finite element. So let me pull in this view, and I'll do something similar as before, and we can look at this as a function of time. We can see this Rally wave going through, and then it will hit that flaw. And just like before, we'll actually see a creeping wave again as it hits the flaw going down that flaw. So that is new The next thing that we have that is new is if we are modeling an austenitic material in a weld. Let's go. There we go. Okay. So we have our austenitic material in this weld, and we see our streamlines. We can compute this with finite element. We could compute this before with semi-analytical models, but now we can check this with our finite element models as well. And we can see our results are quite continuous throughout the weld, which is very, very nice. And this same model we did with semi-analytical algorithms. I'm going to go ahead and pull in the results so we can compare, which is great. Now we can compare our semi-analytical models to our finite element and validate them against our finite element simulations as well. So we can see that even though the semi-analytical algorithms handle this pretty well, obviously the finite element handles this complex material a lot better than the semi-analytical algorithm. So we see it's quite continuous within the weld for the finite element simulation here versus the semi-analytical algorithm. And my last example for the finite element module is going to be looking at a cluster of notches. So previously with our semi-analytical algorithms, we were not able to look at what would happen with a cluster of flaws because CIVA was not able to compute echoes off of different flaws interacting with each other. It could not do that. But with finite element, now we can look at how flaw echoes would bounce off of each other. So let's go ahead and look at the cluster echoes obtained from a cluster of notches. There we go. So we can see all these cluster of echoes from the cluster of notches that were computed with the finite element. Okay. The last thing I would like to show you, going back to CIVA UT, which can be done in finite element. This is our modeling of a weld, complex weld material, is our new way to model weld materials using MENA. That's me. So in our specimen panel under material, before with our welds, our weld materials, when modeling grain orientations, we could take a macro graph and insert that macro graph behind a weld and draw the different grain orientations and orient them accordingly. We could also use the Ogilvy principle. You can still use those, but now we have a new way of modeling weld grain orientations by loading or modeling the welding process data. So you can come into MENA and tell CIVA the number of layers and also the other parameters for welding that you have, and then edit the past pattern and enter in your welding data. And once you have done that, then CIVA will generate the grain orientations based on your welding passes that you have inputted. And it will display it on your 3D view. You can also still view your streamlines if you would like to, based on the welding data and the grain orientations that CIVA will compute from that welding data that you put in. And let me take those off so you can see this a little bit better. There we go. So that is the last feature I have for the new features in CIVA UT. Okay. I hope you enjoyed those. Now we will get back to our PowerPoint and go through CIVA ET. So CIVA ET includes our field calculation tool, where you can look at our field is in the component. Then we also have the probe response tool, which includes impedance diagrams and liftoff signals. Also has the inspection simulation tool and steam generator tube simulation, where you include your flaws and look at the flaw responses. And then you have your sensitivity analysis and probability of detection tools as well within CIVA ET. You have different techniques covered within CIVA ET, include conventional ET, eddy current arrays, remote field techniques, and pulsed eddy current. So what is new in CIVA ET? So there is quite a lot of new probes and geometries within the steam generator tube inspection module of CIVA ET. And we will cover most of the demo within this module. There's also a new probe response module within CIVA ET before the probe response features or within the field computation, or the field computation module. So now this is its own dedicated module, which allows you to actually save this data or these results so that you can load them in later and refer to them later on, as well as drag and drop the liftoff signals onto different data if you wanted to compare between, for example, flaw signals and things of that nature. So now you can do that. You also have a new 1D plotting tool, and you have some new features for management of complex geometries in the inspection simulation 3D module when it comes to scanning. So that is very nice. So we will switch over to CIVA, and I'll give a demo through CIVA eddy current. Okay, so we'll start in our probe response module. And I'll start with our default configuration. Again, we have our specimen in CIVA eddy current. We have multiple different specimen that you can use within CIVA eddy current are available, just like CIVA UT. And then in our probe panel, for the probe response module, you'll be able to model your coils. Multiple different coils are available, as well as the ability to define ferrite and shielding properties for your coils. Then from there, you can define a range of frequencies, or if you wanted to do liftoff and define a range of liftoffs and study those variations, you can do that as well. We're going to study 40 different frequencies between the min and max frequencies and see what those results give us. This will allow us to choose a good operating frequency for this application. And again, if we were to do this for the liftoff as well, that would help us as well to look at liftoff as well for our application. Okay. So here we have our impedance plane. I'm going to go ahead and just zoom in on this section here. And as I change my frequency, we'll see where I'm at in my impedance plane. Again, this will just help me choose a good operating frequency for my configuration. Okay, now we'll go into our inspection simulation module. And here we have a plate. And I'm going to go into our flaw panel. And there'll be a couple different flaws depending on the geometry you're in. You'll see different flaws that are available within this module. And then for our probes, you'll notice that in this module, you have now the plus point like probe, the row test like probe, and the array probe. These were all available before. I just wanted to mention them. And then from here, I'm going to run this configuration, and we'll look at the results with the C-scan defined. So you'll notice that all the cursors are linked. So as I look at different positioning of my probe, you'll see that my impedance plane changes from my C-scan as well as I go over the flaw. Okay, going back into my model, what I want to note here in my specimen panel that if I want to do any tube modeling, that I can only model straight tubes within the inspection 3D simulation part of CIVA eddy current. So if I want to do anything more complex than straight tubes, then I need to go to my steam generator inspection module. This module utilizes heavier computation algorithms, and so the computation time is a little bit longer, but it allows us to do a lot more when it comes to tube modeling, especially when it comes to steam generator tubes. So okay, so here we have quite a lot of advancements in this module. Like I said, we dedicate a lot more time in the demo to this module. So the first thing I want to note is in the probe panel, we have a lot of new probe types. But for our probes, another thing I want to mention for scanning, one of the main things that was updated within the eddy current module in general is that for scanning, now the scanning of the probe follows the complex geometry of the component. So let me change this a little bit so you can see it better. Maybe like, okay. Let me only manipulate it. Okay, right, like that. Okay. So as this scans, you'll see that it follows the curvature very, very well. It was not like this before. It was straight, but now it follows the complex profile of the curvature of this component, which is very, very nice. This is a very, very good improvement. We have a ferromagnetic support plate in this example, which is pink. I really like that it's pink. Pink is my favorite color. So not that you guys needed to know that, but I thought it was important. So, but yes, our support plates are pink and CIVA eddy current. That makes me very happy. And then we have different probe types that are new. So before in this module, we only had axial probe types available. Now we have remote field probes, transverse rotating probes, and cross-wound orthogonal probes, array probes that are all available. So let me go ahead and load some files so that we can take a look at the new features of probes as well as the new geometries available in this module. So the first one we're going to look at is that transverse rotating probe that we were just looking at. And for each of these probes, just like in the other modules, you will be able to define very detailed parameters for each of the probes, including the acquisition for the probes. And the next thing is to look at is the flaw panel. There's quite a lot of different flaws that you're actually able to define within this module. They're not necessarily new. I just wanted to note that you have a lot of different flaws to define within this module. holes, straight wear, bumps, grooves, notches. Within notches, you have lots of different capabilities to define as well. So you have the circumferential notch, which is in this. You have L-shaped notches, T-shaped notches, H notches, and more. So I wanted to mention that. The next thing I wanted to mention is that we have the array probe. So let's go ahead and look at our new array probe. So for our array probe, this would go through this component and through the sleeve that we have here. Or the support plate. I'm sorry, the support plate that we have. And then we have our notch right here. So in our component. So with our array probe, just like previously with our other probes, we would define everything in our probe panel. And we can go ahead and look at the results for this file. So for this file, with our impedance changing, as we go through the support plate, I'm going to go ahead and rotate the result of this C-scan so that it just makes a little bit more sense. As the arrays go through, you'll notice that the impedance will change as it goes through because of the support plate. So you can see in my graphs to the right too, everything's linked. So we are entering into the support plate and a color change, and we have a shift in the graph here as well. And then as we cross over that flaw, that notch, you have a change right there. And we're going through the support plate still, and then we exit the support plate and the impedance changes again. Okay. Then the next new probe that we're going to look at is the plus point like probe or the cross-wound orthogonal probe. So that is also new in this module. And we now have the capability to define a sleeved probe, or I mean, sorry, a sleeved tube. Let me find it. Here we go, a sleeved tube. So here you would be able to define the different parameters for that sleeved tube in pink. And that is new. We still have all of the capabilities for the straight tube, the U-bend tube, and the expanded tube that we've already seen, but the sleeved tube is new. And last but not least, we have two more features regarding geometry. The first one we're going to look at is our clogging, which is in brown. So for our clogging, we can define the material, and then we can define two different shapes for our clogging. As you can see, I have two different clogging shapes. And then we'd be able to define where we want those clogging shapes. So I wanted to define one shape on the left and one shape on the right. And then I wanted the top and the bottom empty for my clogging. The next thing that is new, sort of new, is that we are now able to define the deposit on the outside of the tube for just a certain section of the tube. Before, if you wanted to define a deposit, it had to be on the full length of the tube. Now you can define it for just certain sections. All you would have to go to is the tube panel and hit activate deposit, and then basically define the different parameters and say where you wanted it on the tube, for example. So now you can limit it to a certain section of that tube, which is very, very nice. And it's more realistic for your applications. Okay, that is it for new features in CIVA ET. And let's get back to our PowerPoint and go into CIVA RT. So for CIVA RT, we have our radiographic image simulation for direct radiation and scattered radiation using the Monte Carlo method. We also have our sensitivity analysis and probability of detection curves. The different techniques that are covered are X-ray, gamma ray, high energies, and tomographic reconstruction with different algorithms. So what is new in CIVA RT and CT? So we have a quite large material database that is new from NIST and the ENDF libraries. We also have a new spectrum generator called Specky. I personally really like the name of that, but I will show you that. It's quite fast, which is really, really nice. We also have 2 new interactions that are available under the Monte Carlo scattered radiation area, the Bremsstrahlung and the X-ray fluorescence. You would enable Bremsstrahlung if you have a thicker component that would interact with the specimen, the scattering interacting with a thicker component, and then the X-ray fluorescence would be used for a heavier material. So just keep that in mind when you are modeling. Then also the Monte Carlo model was optimized for faster convergence through variance reduction. So that is super nice as well. We have some new defects that are available in CIVA RT-CT, which are cluster porosity, which I will show, as well as the parametric crack, which I will also show. And this is also a very, very cool new feature. We now have the ability to have data fusion where we can load in an experimental image, X-ray image, into CIVA RT and then merge it with a virtual flaw. So this can be very, very beneficial for machine learning, creating data sets for that, as well as AI training. We also will be having a photon counting detector included in a later release of 2025 CIVA patch. So let me switch over to CIVA for a demo on CIVA RT new features. Let me go ahead and start with a default weld configuration in X-ray with this film. So we have our emission cone and our weld with that new parametric crack. And our specimen panel, we'll see where we have our weld. And I'm going to go ahead and go to our material and start with showing you a new material library that has many new materials from NIST and ENDF. So I'm going to go ahead and select the stainless steel 316 for my simulation. And then I'm going to expand this to look at the different components that are in my alloy. And from here, we can actually look at the percentage of each component, and I can edit these accordingly if I would like to. If I know the different atoms that are contributed, I can also edit it that way as well. I can also, if I wanted to switch out the different components that are contributing to my alloy, I can do that by clicking into the Mendeleev table and click on a new component and add it in that way. One of the new things in CIVA RT under the materials is that you can now actually look at the alloy attenuation versus energy for the whole alloy and not just the specific components. So if I wanted to look at the attenuation at a certain energy level, I can go ahead and do that here. So that is new and super, super nice as well. The next thing that is new, we're going to go ahead and look at that Specky generator by going into our source parameters for our X-ray tube, and we're going to click on modeling. So you can model your own if you know your anode material, your anode angle, and your acceleration voltage. So I'm going to go ahead and change this just so you can see it update real time. As you see, this is updating as I enter in new voltages. So it's very, very fast. So that's very, very nice. So that is new. It also has more energy levels as well now, so that is nice. Okay. The next thing I want to show is our flaw panel with our new parametric crack. We'll focus in here. You have 10 different parameters here to basically make this look like your parametric crack, whatever you're seeing in the field, and you can model it to look very realistic. I'm going to go ahead and position this a little bit differently within my weld for my X-ray shot. And that looks good. And from here, I'm going to go ahead and show you where the new Monte Carlo options are. So if I do compute Monte Carlo, here's the Bremsstellung and the fluorescence effect that are available. I am not going to compute Monte Carlo for this because it will take a little bit too long for this demonstration, but I just wanted to show you where those are. So I'm going to go ahead and run this file here. Okay, here we go. We have a very fast computation and my X-ray image here with a parametric crack that looks very realistic through my my weld. So this is really nice to generate lots of different images like this for your different databases if you are trying to build databases for machine learning. Okay, the next thing I want to show you is our cluster porosity as well as data fusion. So I'm going to show those pretty much at the same time, or step by step, but at the same time. Okay, so our cluster porosity is a new flaw, our second new flaw type within CIVA RT. It allows you to define a region where you want to include cluster porosity. And then you can define a minimum radius for that cluster porosity and a maximum radius for the cluster porosity you want to define. And then you can define a targeted volumic density. So as I edit this, you'll see on the right in the 3D view, this will change as I define a new project. Okay, so you saw that it changed over here to the right. When I change it again, you'll see that it will change on the right in the 3D view. Okay, so that is new. Very nice to be able to define cluster porosity. The other thing I want to mention before I run this is I'm going to go ahead and show that I'm going to have some grain noise defined on my detector to make this more realistic in the simulation. And I'm going to run this. We'll take a look at what this looks like as a simulated case. And then I will go back into this and look at the data fusion. So here is my simulated case with the cluster porosity and the simulated grain noise. Looks pretty good. Now, if we wanted to do some data fusion where I want to load in a real experimental image without cluster porosity, for example, but include my virtual cluster porosity flaw on top of that experimental image, that is what I'm going to do now. So the first thing I'm going to do is I'm going to take away that grain noise because I no longer need it on my detector because I'm going to be loading in an actual X-ray image and lacing that with my cluster porosity. So I'm going to take that away because I don't need it. And I'm going to go into storage, and click experimental image fusion. And I'm going to click here to choose my TIFF image. And then here I'm going to enter in two parameters that you need to do. So my linear attenuation coefficient for this TIFF image and then the maximum thickness gap crossed. So here, I believe I'm going to get that from my geometry. Let's see, the top bead height, so that dimension here, that gap, so 1.3. Maximum thickness gap crossed, 1.3. Okay, so those are the two things I need. Then I can go ahead and run this. And CIVA will be able to compute my cluster porosity and give me that image. And then I'll be able to pull in my augmented image where it will take my TIFF image. So this is just the cluster porosity. And now I'm going to pull in my augmented image to the right. So this is my cluster porosity with that experimental image data fusion that we see on the right. So those two are fused together. Okay, so that is pretty exciting, especially if you're trying to build some pretty large databases and you need some more flaws within those databases. This is very, very helpful to create some realistic images. Okay, that is all I have for new features in CIVA RT. Let's go back to our PowerPoint. Okay, CIVA guided wave. So we have our dispersion curve computations. We have our field computation module where you would put different cross sections throughout the component and look at our field at those different cross sections. Then you have your inspection simulation tool, again, where you would include different flaws and look at the response off those flaws. You have your sensitivity analysis and probability of detection curve computation. This module covers various different specimen geometries for different applications like rail sections, as well as if you have buried pipelines. Let's say they're going through water or going through cement and you can't access them, you may want to use guided wave. So this would be a module where you can simulate something like that. And then you have the ability to simulate piezoelectric magnetostrictive or EMAP probes, as well as single element or array probes. So what is new in this module? We are now able to compute the effects of surrounding medium can be accounted for in the field computation module. So like I mentioned with buried pipelines in water or in cement, now in your field computation module, you can take this into account around your pipeline, like you can see in this image to the right. That would actually affect your results in the field. This is not available to consider in the inspection simulation module yet, but it is available in field computation. For your inspection simulation module, you can now have a fluid layer medium bounded by two solid plates and account for that. So that is very nice. And you can also now include solid inclusions in the inspection simulation module. You also are now able to compute anisotropic materials or model anisotropic materials in all components for the mode computation module only. It is not available in the field computation module or the inspection simulation module, but you can do it in the mode computation module and model those anisotropic materials. For CIVA structural health monitoring by guided waves, we have dispersion curves computation, and you have your inspection simulation tool, which is based on spectral finite elements with very competitive performances. You have multiple sensors now with structural health monitoring, where you have sensors transmitting and others receiving, and you may do this simulation or with a flaw or a component free of flaw, and then you would run these simulations and reconstruct them in a 3D view. And then within this module, you have the sensitivity analysis and probability of detection tools as well. This module covers metallic and composite plates, pipes, and elbows. It can account for curvatures, stiffeners, and sleeves. And for your defects, it has holes, cracks, delaminations, corrosion, erosion, and inclusions available. So what is new for this module? We have some new defects, like flat bottom holes, and then for erosion in the erosion and corrosion flaw, it is now available in all structures, including the multi-layer capabilities, whereas before it was only available in a couple different structures. Now it's available in all. We also have a new C-shaped stiffener option, as well as in the other stiffeners, you're now able to, at the ends of them, basically taper off the edges of the stiffeners, which is nice. And before, you could only model one stiffener or one sleeve at a time in the component. Now you can model several sleeves and stiffeners on a component at a time. Another new feature is to add the new boundary condition onto a component. So what this does is it enables you to define a smaller component. Let's say you have a very large tube or a very large plate that's basically infinite, and you would not expect to have reflections off of the edges of this component or any signals of that nature. But with a structural health monitoring module, you wouldn't want to make the component as large as it actually is because it would increase your computation time. So you would define it as a smaller component. And in order to not get reflections off of these edges, you would include this new boundary condition so that it would absorb those echoes and not have the reflections, and basically make your component infinite in a sense. Last but not least, you are now able to import your experimental data into your structural health monitoring tool and benefit from the different capabilities of the CIVA structural health monitoring module for your experimental data. Okay, for your parametric studies, metamodels, and POD features that are available in your different modules, CIVA has these tools to help with lots of very, very fun things to do. I personally love these different tools. I think it makes CIVA very robust and very, 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 very helpful for predicting worst case scenarios, best case scenarios, and modeling and varying parameters to define and model probes or optimizing your inspection cases. So for your parametric studies, this allows you to define variations on your parameters to study their impact. So let's say you have a flaw height and you want to vary that height, and you can look at how that impacts your results. The next thing you can do is have a meta model. This allows you to generate as many samples as you wish. So what this means is, let's say you do a variation study from 1 millimeter to 10 millimeters on a flaw height. You can then generate a continuous amount of samples between that range and have the result of an amplitude off of that flaw at 1.2, 5.3 millimeters, for example, of that height, and look at how that would impact your results and have a continuous amount of data in that range, for example, for multiple different parameters. And so this will allow you to predict worst case and best case scenario. Some people call this surrogate modeling, for example. This also would allow you to estimate your different influential parameters as well. Then you have your probability of detection curves, which is included as well. And this is very nice because you can use your simulated data sets to generate your probability of detection curves, or you can load in your own experimental data into CIVA and utilize the probability of detection tools in order to build your own probability of detection curves with your own experimental data. All of these tools are available with the different modules that we have covered today. So if you get CIVA UT, you have access to the parametric studies, metamodels, and POD features and tool sets, along with eddy current has all these, guided wave has these, structural health monitoring has these, RT and CT has these as well. So what is new with the parametric study module? So now you can do multiple extractions from a variation, whereas before you could only choose one. So for example, with UT, If I was varying a parameter, I could only extract the maximum amplitude or the full signal results. Now I can choose to extract both of those and more, and then just switch between these results after the fact. So before I would have had to generate the simulation twice, but now I do not have to. I can extract both of these and just switch between the two in the results window if I wanted to look at the results and the extractions for both of these. So that's very, very nice. The next thing that is new is now I can look at all of my graphs in this window and display my data in dB or percentage. Before, I could only look at the dB and percentage in the 1D viewer only, and the rest of the plots were in raw CIVA points, but now all the graphs can be viewed in dB and percentage as well, which is very, very helpful. And I think this is probably one of my favorite new features for this parametric study module, is now that you can view all those different cases as a table. And this will allow you to sort on the different columns and identify your best and worst case scenario. So before you still have it, you had that graph with all of the lines that were pink and it kind of looked like a big spider web. Now you can switch the view to table and sort on different columns to look at your data. You can also export this as well. Okay, for your POD features, what is new? So it got a little bit of a remodel to it, so it's a little bit more user-friendly, which is really nice in the analysis page. And then you also have a new probability of detection statistical model called the Nordtest TR394. You also have a ability to now do false alarms, and you can either add in your own noise parameter, or you can have CIVA model in a distribution type for your noise. And then you can compare your PFA curve to your POD curve and have CIVA compute the ROC, which is here on the right. Then you have one more feature, which is the 2D POD, where you can take two characteristic parameters and see a 2D POD plot of those two characteristic parameters in a 2D POD. So if that was very interesting to do, then we invite you to join us for one of our training sessions. If you have any questions or are really interested in learning more about any of the different modules, please feel free to reach out and join us for one of our intercompany training sessions. If you're interested in having a training at one of your facilities, also please feel free to reach out and we will come to you. These are the different dates we have available. We also have these dates on our website as well. This concludes the formal presentation of our webinar.